Okay, this is 7.4, Similarity in Right Triangles. Our objective today is to find and use relationships in similar right triangles. Now, one of the most important things for you to understand is that when you draw an altitude to the hypotenuse of a right triangle, you form three pairs of similar right triangles. So remember, the hypotenuse is the side that's opposite the right angle. The altitude goes from the vertex to the opposite side and forms a right angle. So CD is an altitude, and it divides this triangle into three similar triangles. So let's take a look at Theorem 7.3. Okay, so Theorem 7.3 says the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle, which is this large one, and to each other. So I have some triangles. So what you do when you do the hypotenuse, so I'm going to take this and I'm going to just drop it there. Let me get up here so we can see it better. So this is triangle ACD. And okay, here's my big triangle. Okay, so these three triangles are similar to each other because CD broke it down. So here are the individual triangles so that you can see that they're similar. Okay, so let's take a look at problem number 1. What similarity statement can you write relating the three triangles in the diagram? So here is our diagram, and we know that YW is the altitude that goes to the hypotenuse of triangle XYZ. So this lets us know that we can use Theorem 7.3. So what they've done is they have taken the large triangle, the medium triangle, and the small triangle that was made. And they've placed them all where you can see how everything lays out. So we know that triangle XYZ is similar to triangle YWZ, which is similar to triangle XWY. So XYZ is similar to YWZ, which is similar to XWY. So now we're going to begin talking about the geometric mean. So one thing that someone thought up was when we have, this is our traditional proportional setup, is that the extremes go from the numerator to the denominator, and the means go from the first fraction denominator to the second fraction numerator. So the 3 and the 4 don't make any difference in this case, but we're just looking at the location. Okay, so geometric mean occurs pretty regularly with geometry. So proportions in which the means are equal occur often in geometry. The geometric mean of A and B, for example, is the positive number x such that A over x is equal to x over b. Now I'd like for you to notice the location. Okay, so let's go on to problem 2. So we need to find the geometric mean of 6 and 15. So 6 and 15 is going to be my A value and my B value. So 6 over x is equal to x over 15. So I'm going to cross multiply, so I get x squared is equal to 90. So how do I solve for a variable that's squared? I'm going to take the square root of it, right? You've got to do the opposite if you want to undo. So I'm going to say square root of x squared, square root of 90. So now I get x is equal to the square root of 90. Well, I'm going to break 90 down to 9 times 10. Why did I choose those two numbers? Because I can take the square root of 9. So x is equal to square root of 9 is 3. So 3 square root of 10. And that's it. Okay, so this is just to kind of help you see how things are related. So they are saying that triangle SQP is similar to triangle SPR. So we're going to put short leg over short leg, long leg over long leg. So it's just so that you can see the relationship. So the short leg was SQ, and the short leg in the larger triangle was SP, and the long leg in the smaller triangle was SP. So, oh look, those are equal. So SP is your geometric mean. Okay, now if you were thinking that when we looked at this short leg, long leg, that PR was the long leg and QP was the long leg, in a right triangle, it's two legs and the hypotenuse. And the hypotenuse is always opposite the right angle. So the legs are SQ and SP and SR and SP. So that's why QP and PR, they're not considered legs, they're the hypotenuse. Okay, so let's take a look at this corollary to Theorem 7.3. The length of the altitude, the hypotenuse of a right triangle, is the geometric mean of the lengths of the segments of the hypotenuse. Now let's just look more in depth, because if you're like me, that doesn't mean a whole lot to you. So let's look at what they've got in the example. So they say the small triangle, they're like, okay, 2 to 4, short leg to long leg, is equal to short leg to long leg. Oh, now this I can wrap my head around as long as I can see the pattern. So what is the geometric mean? It's 4. What is 4? 4 is the altitude of your larger triangle. So the purple, the 2 and the 8, are the segments of the hypotenuse, and 4 is the altitude to the hypotenuse. Okay, let's take a look at corollary 2 for theorem 7.3. So bear with me, there's a lot of words here. Okay, so the altitude of the hypotenuse of a right triangle separates the hypotenuse so that the lengths of each leg of the triangle is a geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to the leg. Okay, so CD is our altitude, correct? I know it's the altitude because it goes from the vertex to the opposite side and it forms a right angle. So with all of these words, what they're saying is AC is a geometric mean and CB is a geometric mean. So the legs of the larger triangle are the geometric mean. So let's go ahead and look at this part. So it says AB to AC, so that's this long length, to AC is equal to AC to AD. Where AC is my geometric mean. Now let's look at the next one. We have AB to CB is equal to CB to DB. So the big one and then the small one. And I know this is slippery and it'll clear up the more we do it. Okay, so the book gave us this diagram to help us remember, and if this works for you, that's great. If it doesn't work for you, that's okay too. So just giving you this in case it's helpful. So for corollary 1, like we're going to start with the small triangle, and it's going to be short leg for the small triangle, short leg for the bigger triangle is equal to long leg for the small triangle over long leg to the big triangle. Okay, so corollary 2 is a little trickier. So be sure and pause and rewind and stuff as you need. Okay, so H, you'll notice H is the hypotenuse of my larger triangle. So it goes to the hypotenuse, we're going to do the smallest one first, to the smaller triangle. So we're going to have H to L1 is equal to, and then we're going to say the leg of my big triangle to the leg of my small triangle. So it goes H to L1 and then L1 to S1. Now let's see if we can write that again. So for this next one, what are we going to do? It's going to start out with H. Let me get a different color. H. Now this time we're going to do the larger triangle. So that's going to go to L2 is equal to, we're going to say the leg to the leg. So H to L2, and then from L2 to S2. Okay, so now in this we're going to use these corollaries, and we want to know what the values of x and y are. So I'm a creature of habit, so let's find x first. So I'm looking at where x is located, and it's the hypotenuse of this smaller triangle. So I'm going to use corollary 2. So I'm going to use this, my 12 plus 4 to x is equal to x to 4. Hypotenuse to hypotenuse, and then leg of the large triangle to leg of my small triangle. So now I'm going to cross multiply. So I'm going to get x squared. See, 12 plus 4 is 16, and 16 times 4 is 64. I'm going to take the square root of both of these. So x is equal to 8. Now let's take a look at y. So for my y value, I'm going to look at where it's located first. Okay, so my y value is on the altitude, so I'm going to use corollary 1. So on my small triangle, I'm going to do short leg of the small, short leg of my bigger, so y is my short leg, is equal to long leg of my small triangle over long leg of my big triangle. So then I get y squared is equal to 48. So now I need to take the square root of both of these. So the square root of y squared is just y. And 48. It's not a perfect square, so let me go over here and let me break it down. So I have 2 times 24 is 48. Now I'm going to do my factors of 24. So then I've got 2 and 12. 12 is equal to 2 times 6. 6 is equal to 2 times 3. And I'm going to pair these up. So I've got a pair of 2's and a pair of 2's. Pairs go out, singles stay home. So what is 2 times 2? So that's going to give me 4 times the square root of 3. And that is what y is equal to.